All right, everyone, we're going to get started again. And can I borrow this just for a picture? Next up are two of the invited papers. And first off is Markus Lumpe from Iowa State talking about Classbox integration into .NET Framework.
Thank you very much. This is actually Thank you. This is actually joint work with my students André Lokasari and Hua Ming, who are also here in the audience. Oops. I will start with the problem that we try to address, and one of the things that we can observe in modern programming language, modern object-oriented programming languages, is that they're not powerful enough to express many useful forms of incremental modification. So I was somewhat concerned now to start with that problem statement, because we have heard today a lot of arguments that there are many useful forms of programming language abstractions for extensions. We have seen the extension methods for the C# 3.0. We have also seen the nice talk about the Python. But I stick to that claim because the current version of C# and including Java and C++, that is still the case. And one of the things that we want to use, or we believe that can solve that problem, is of course class extensions. And one of the major problems with current inheritance methods is basically that you can add new classes to the system, but it's almost impossible or hard to add orthogonal behavior to a class hierarchy. Of course, we have one well-known method to add orthogonal behavior to a class hierarchy. That's the visitor pattern. So we plan for extension, we implement the visitor pattern, and then we can add new behavior to a class hierarchy. But the better method is actually to use class extensions, first and foremost because they allow for modular refinement of an existing class hierarchy. So we basically define it in a class extension and apply it to a class different or specified in a different compilation unit than the class was defined. So we don't have to touch the actual code. We simply specify a new specification unit and apply a new class extension to that class hierarchy. And I have here a picture to illustrate this mechanism. Basically, we have a class hierarchy, and I have here a very simple class hierarchy of two classes, and I want to change the superclass by adding a new behavior. In the normal way, what we would have to do is we take this class hierarchy apart, create a new class hierarchy, and have then to redefine all the subclasses of the new superclass, because we don't have the means to propagate that extension to the existing class hierarchy. So that is the problem. But what we really want to do is we want to exchange, or we want to add or alter the superclass and want that change to propagate to that particular class hierarchy. That is the goal, and that would be nice to have in a programming language. When we do this, we face one problem, namely that extensions may have global impact. And one of the things that I noticed with the extension method in C# is that we face the same problem there. We can apply this to, we can load a classic an extension method into the current scope, but that extension method may impact the whole scope. So we really need to look out for a method to control the scope. And this is one of the things why class extensions are not good at all, not always good. We really need to have a new scoping mechanism to control the visibility of that change. And only if we are able to control the visibility of that change, we really truly benefit from class extensions. And one example to illustrate this is as follows. So we assume that we have an existing class hierarchy or an existing package of services or classes or whatsoever, like this, in namespace A, and we want to create a new application. Let's say we want to produce a new version, extended version of that same functionality. So what we do is we simply create a new namespace, or in the Classbox terminology, we create a new class box import the required classes that we want to export from that class box to the user, and specify our extensions within that class box. The extensions are applied to the class within this and can only extend to that class box and clients of that class box. They don't pollute the originating class box space. So when looking at that picture, two class boxes or two systems can coexist, and we have the old version and the new version, and the new version has the same structure as the original plus the additional behavior, but this additional behavior is confined to the new class box. That is the actually idea of the class box concept. And to summarize the basic properties of the class box concepts is that the class boxes define an explicitly named scope to manipulate classes. When I say manipulate classes, it actually means I can import classes, I can build new subclasses, and I can extend classes. Those are the three basic operations defined in the original class box concept. And the second point here simply specifies that all the extensions that I can specify on classes are local to the current class box. They are only visible to the class box itself and all clients that are explicitly using that very same class box. So, we did not develop the class concept. This was work done in the University of Bern in Switzerland, and they came up with an implementation for Smalltalk, and they also presented a Java version of the classbox concept, which was basically an interpreter that translated the Java code, extended Java code into pure Java classes. Our idea now was, okay, is it possible to apply the classbox concept also to the .NET infrastructure or to C#? And when I say .NET, I mean C#. I wanted to test the hypothesis that we can use the classbox concept with C#. And when I say I wanted to test it with C#, I also wanted to do something very naturally. I didn't want to change the C# language too much. We only wanted to use some of the classbox. We wanted to use the classbox concept and wanted to define a minimal extension to the C# language. And here the extension that we have specified. So the classbox concept defines three operations: class import, subclassing, and class extensions. And in order to represent the classbox operation for import, we basically hijacked the using alias directive in C#. So if you know C#, you can specify using, then introduce a local name equals the original name. And this would simply provide you with an alias for the same class. It would not actually import that class. It simply adds some reference to that class to the current compilation unit. And to my knowledge, this using statement hasn't been used very frequently in C# at all. So it was a safe bet to simply hijack that. So what we did is we simply have overwritten the semantics of the using alias and simply use it for our purposes at the moment. In the later development, we may actually define our own import directive and preserve the original semantics of the using alias data. Subclassing is the same as in the standard C#. You don't need to change anything. And the last but not least, there is this class extension. And of course, class extension is combined with import, which means we have simultaneously an import and an extension applied to that class. So we use the same using alias directive and simply use an include clause to specify the corresponding extensions. And
so Marcus, I've got two questions.
Yep.
One, you said you hijacked the using alias.
Yeah.
Did you write a preprocessor?
Oh, okay. We used the monocompiler. And basically changed the front end of the monocompiler. What we did, we added the new syntax for the class extensions to the monocompiler, and we changed the semantics of the using statement. So basically what we added the class extension operations to the monocompiler, process those, run the extensions through the compiler by using the standard mechanism built in the monocompiler, and emit standard .NET assemblies as produced by the monocompiler.
Okay. And the second question is, these class extensions, are they limited to adding new methods, or can you actually add new member?
Yeah, and original Classbox concept limited the extensions to methods only. We immediately extended this to members, so you can basically define a new class body as part of the extensions. You can define state and methods, and everything is supported. The only restriction that applies to that extension is members have to be public, and methods have to be public, and instance variables have to be private, because if we would allow for public or protected instance variables, we would run into problems known as the diamond property with multiple inheritance. This is one of the restrictions that we apply. The compiler actually checks that property, and if nothing is specified, it assumes those visibilities, and if they are specified, they are checked and refused if they are public.
Okay, one more question. When does this extension process occur? Does it occur at compile time, or can it occur at runtime?
This extension process occurs at runtime. So what we do is we process the specification, we compile the extensions. Basically what we do is we create new subclasses for those extended classes in the compiler, and we integrate the resulting extended classes into the class hierarchy into the resulting class hierarchy. And that is actually our contribution, because since we create new subclasses for extended classes, we would break the inheritance relationship between the original class hierarchy. And our contribution is to rewire the inheritance graph to bring those classes into the class hierarchy back. The original Classbox concept did this at runtime, and this was the only purpose why it took place at runtime. They created a specially designed method lookup mechanism that checked at runtime if the providing Classbox defines an extension. And if the providing Classbox defines an extension, then they simply reroute the method call to the extended method that took place at runtime. This was one aspect that I think was due to the original implementation, which was done in Smalltalk. And Smalltalk is a very good candidate for that approach. But if you look at the C# language and the .NET infrastructure, this isn't actually good and does not actually work. One of the things that we noticed is in .NET, you need to know the type of a class when you load the assembly. You cannot create a dynamic class. Correct me if I'm wrong, but you cannot create a dynamic class at runtime in .NET. Of course, you can create if you compile that code and load the assembly but you have to have a type and metadata information in the metadata for the .NET assembly before you can use that type. So when you load the type into the VM, you have to have a well-defined type. The Classbox concept in the original definition simply constructed the type at runtime, and we moved that process from runtime to compile time by preserving the original Classbox semantics. And we're gaining also a performance boost, because now we don't have to look for every method whether or not it occurs extended. Now every method can be called in the original way, and even all the extensions are built into the code at compile time.
The emit
Yeah.
is of the runtime could help you emit metadata.
Yeah, that's what I said. So basically, in order to do this, I would have to compile or emit the information at runtime. But the idea that I had, or that we had at the beginning, was: is there a chance to integrate the extensions at compile time, and by integrating those extensions at compile time, gaining or regaining the original, or recovering the original method lookup mechanism, so using the original method lookup mechanism, and therefore eliminate all the runtime overhead associated with Classbox method lookup. And that is our contribution. This is a tiny example. I call it actually my canonical example because it's not very exciting. It's a point class, but it illustrates basically everything that you can find in a Classbox concept. On the left side, we have a tiny class hierarchy with a point and a bounded point, that they are in a subclass relationship. And in the middle Classbox called linear Classbox, we simply import explicitly the class bounded point to define a linear bounded point. And one of the things you will notice in the dotted borders, we denote classes that get implicitly imported in the Classbox concept. This is one of the major differences between standard import mechanisms and the Classbox mechanism. Classbox import will import everything. There's a transitive import in the module because you have to change all. You have to consider all the classes in a Classbox hierarchy. So in this case, even though we only import explicitly bounded point, we will also implicitly import point, because point may actually be affected by a definition or by an extension in that linear Classbox. In this case, it isn't, because we have only defined a new subclass, linear bounded point. And the interesting Classbox is actually on the right side, left, which is color CB. In this case, we explicitly import point and linear bounded point, and observe that we import point from the point CB and linear bounded point from linear bounded point. And since there is a bounded point in between, the import will implicitly also import bounded point, but in this case from the linear CB or point CB, it doesn't really matter. It will be imported because this is the class that is the same throughout all the class boxes. And within the Classbox color CB, we define an extension to point. So the idea is here that we add a color property to point, and all classes in the color CB will now possess a color property. And the color has a method and also a property. As a property and also a private instance variable, so to record the color property. And one thing additional to the import, and here only explicitly imported classes are visible. So the user or client of color CB will only be able to instantiate linear bound instances of linear classes, the classes linear bounded point and point. Bounded point itself, in the class in the middle, is invisible, but it's there to make that inheritance graph complete. So to illustrate extensions, simply look at that running code, C# code, extended Classbox aware C# code. In the first, we define an extension. So here we import the class point from point CB and add some additional behavior. The color property, it's very simple. This is an import and extension, and in pure import that is does not define any extension is defined in the last line. So with the last line, what we do is we import linear point, bounded point from linear CB, and by importing that class explicitly in that class box, we make that class box, this class also possess a color property, because it's now subject to the extensions defined in color CB. That is the idea. So, as I said, existing implementation suffer from a performance overhead from 25 to 60% in the method lookup, which is acceptable for a research project, I would argue. But for an industrial strength language, this is not a good idea. So our motivation was actually, how can we promote the Classbox concept to an industrial strength concept so that we can use it in a language like C#. And one idea that we came up with was that the .NET infrastructure uses actually a virtual execution system. So it does not lay out the classes directly. It actually asks the virtual execution, the system or the just-in-time compiler to lay out the classes. So before that, we can change everything that's available to us. So basically, our idea is we consider the metadata emitted into the assembly as a program. And by using that assumption, we can rewrite the program to integrate our extensions into an existing class hierarchy. So we basically say we produce an assembly and take that as a program that we can rewrite to really produce a class box in the end. So what we do is the front end or the C# compiler compiles the class box specification into an assembly. And in this case, the assembly will contain that class hierarchy, and we observe here that the color CB point, which we have defined here as a new subclass in the color CB, is not in the inheritance graph of linear bounded point. That is what standard techniques do. We introduce a new subclass, and that new subclass is not in the inheritance hierarchy. We use now our tool, which is rewire.net, to transform that metadata and create a flat class hierarchy. And this flat class hierarchy corresponds to the structure of the class box. So in this inheritance graph, we see that color CB.point is in the inheritance graph of linear bounded point. And by adding that to the inheritance graph, now linear bounded point possesses also the color property. So clients of point now benefit from the extensions defined to point. That is the idea. And this occurs in metadata. So we transform basically the metadata. But if we do this, we destroy the integrity of the assembly. This is the first question. So if we change the metadata, which is correct, now we actually destroy something, or we bypass the security checks, so something eventually goes wrong. And in this case, something goes wrong, namely we break the integrity of the constructor. The constructors in C# cannot skip class initialization. So you have to call the direct superclass constructor in every constructor. But once you notice that, you have the means to correct that mistake. So what we actually do is we locate the call for the super constructor in the constructor code bytecode and simply take the method descriptor that denotes the superclass constructor and replace it with the correct one. And by replacing it with the correct one, we restore the integrity of the bytecode. So, and our transformation in the bytecode can be verified. We start with correct bytecode and we produce correct metadata. And after fixing the constructor code, we also get correct verifiable bytecode. So we transform assemblies and produce correct .NET assemblies. And to accomplish this task, we have defined a CLI package. And here, this is yet another PE reader and writer. I'm sorry, I was surprised to see this again. But one of the things, we did not do this on purpose. So we didn't invent yet another CLI reader and writer package. We simply looked at what is out there and can it be used for our purposes. And unfortunately, there was nothing out there that could be used for our purposes. We needed an PE reader writer with symmetric reading and writing capabilities, and we also needed a facility to access bytecode and to change bytecode, but not the full-fledged bytecode emission that is part of the emit package. We only needed to be able to read bytecode and change method descriptors. That was it. But the most important part was symmetric reading and writing of assemblies. And what this package actually provides us with is we can manipulate metadata, we can fetch bytecode, and we can replace it, and everything is provided in an object-oriented view. Yes?
Is code signing affected at all by this?
There are some things that are affected. Code signing is probably one thing. Debug information is not retained. We have to effectively eliminate debug information because it breaks the rewiring process, breaks the debug information, and so far we haven't been able to recover that because honestly we don't have the documentation. I don't know how the debug information is specified, and I had to throw it away because I don't know how to regenerate debug information. It's not public, underneath to my knowledge. So certain things, we lose certain things. but we create new assemblies, and if you have to sign that new assembly, you can probably sign that assembly again. But for our purposes, we only looked at the way to produce correct assembly that can be used in the program. So we produced a verifiable assembly.
This also means that you can't put it in the action, right?
Pardon me?
You wouldn't be able to put any assemblies that use this mechanism in the assembly cache?
To place it in the cache,
Yeah, the global assembly.
the global assembly cache. Honestly, I haven't tried it yet, but there is probably a way. We haven't studied that problem yet, so we only looked at assemblies in our in file space, and we didn't look at the global assembly cache. But I believe that it would be possible at one point if we take the right steps. And to illustrate the picture, we take our input, or we take our input, feed it to the rewire.net, which is a tiny tool that uses the CLI package and produces a set of assembly that corresponds to the physical structure of a class box. And basically, what we have accomplished here is we have come up with a feasible solution for virtual execution system and the Classbox system. Moreover, we can take standard .NET assemblies, given the fact that we may lose some information, treat them as class boxes temporarily, extend the classes defined in those class boxes, and emit code that is, again, a standard .NET assembly. It's not a special assembly. It's a standard .NET assembly that can be used in another application as it was defined in standard C#. So we really produce standard .NET assemblies. There's no runtime overhead. And as I pointed out earlier, it's a faithful implementation of the Classbox concept. So even though we changed this from the runtime lookup to a static resolution, it's a faithful implementation of the Classbox concept. And while we were doing this, we saw a huge potential to do even more. We have only done some conservative things to change the metadata, but you could envision even more. There is a chance to completely restructure a class hierarchies, to take everything apart and put it back together, and you can do it in a way that preserves the verifiability of an assembly. You can take everything apart and do something more than you can physically remove classes. One of the things that we always face is we can always add something, but we can never really remove something. But by doing this at the metadata level, we can remove safely stuff from a Classbox hierarchy, from a class hierarchy. And
One last question about this. Is it just to use as a way to defeat a licensing mechanism, though?
that was not our goal. Okay. To be truthful or to be honest, I believe so. Of course, it can be done. It takes some energy to do this, and it only takes energy to defeat any security measurement that you can find nowadays, and it might be possible. We haven't advocated that. So our goal was to add functionality and to make it happen, but if this is a concern, we haven't looked at this, and this was not really our concern. And one of other things is we also require non-obfuscated assemblies. We may be able to deal with obfuscated assemblies, but we haven't looked at that because I don't really find it necessary to obfuscate the structure, because if I want to do it, I will find a way to figure out the information. This was one of the things.
Yeah, but actually, on the .NET framework, it's installed most of the assemblies put in the GAC, they are GIT'd already there.
I know this is an interesting question. So the point is, what you're making is, when you install assemblies, they are jittered into the platform. But now think about a use case, and that is one of our arguments, when you have the assembly not jittered, if you still have the managed assembly and you want to install or deploy that assembly on an embedded device. and it's a user-specific embedded device. So our idea is that you can define the user extension or the specific device-specific extension for that device, created as a class box, and then deploy both the original assembly and the Classbox extensions on the embedded device and JIT it to the embedded device, because you don't need the flexibility anymore, because once it's deployed, it won't change. That is what we have. So we get standard assembly that can be transformed to native code on the embedded device or the target device, and you don't need to change them anymore.
So you cannot make extensions for system assembly?
Yes, you can. In the in the 2.0 version, most standard assemblies are managed assemblies. This is a bit with difference. Correct me if I'm wrong, but in the version 1, most standard system assemblies were native, and in the 2, yeah, a lot of okay, if I'm wrong. But with the .NET Framework 2, I think that most of the assemblies are managed, and you can extend the managed assemblies also in the system. Of course, we have to deal.
They are GIT when they are installed,
No.
They are managed, but they are GIT. So it means that they are compiled. There's no GIT when loaded. Maybe I don't know the mechanics.
Yeah, but it only be used for, let's say you have a system assembly, you create extensions for it, and then it's only the users of the extended ones that are going to look
Yes.
at this new environment. So it may still be workable. Even if you're
Yeah, the point is, of course.
the new hierarchy.
Yeah, the point is the Classbox concept has not been defined for, or is not part of the .NET framework. So what we are saying is we have used the standard .NET assembly mechanism and provided an extension so that we can represent Classboxes. If you really truly want to support Classbox in the .NET framework, you have to take steps and integrate the mechanics into the .NET assembly. But it doesn't mean that you have to change much. You simply have to provide the necessary things so that it can be extended. That is our idea, or the dream that we have. And I think it doesn't take much to enable that technology.
So this morning, Anders was talking about extensions that are coming to .NET 2.0 facilities. Can you please give us some comparison? What's going on there? Because it's understood from his talk. He was talking mainly about syntactic sugar kind of thing in C#. Yours is something like on the assembly level, on the intermediate language level. So, can you please
No,
give some comparison?
it's not on the intermediate language level. It's syntactic sugar. You add Classbox language abstractions to the C# language, so it's the same as adding syntactic sugar, but those extensions require something else at the level of the assembly, not at the intermediate level, at the level of the assembly. So we need to rewire the assembly structure. That is the thing that we need to do. Because we import an existing class hierarchy, we have to inspect that existing class hierarchy and integrate the newly defined extended classes into that class hierarchy. That's the only thing that we have to do. And that step happens at the level of the assembly after the compiler has emitted the code. So we perform those steps on the assembly, not on the intermediate representation. There might be a chance to do this in the compiler. So if you load all the assemblies and have an internal representation and do this again in the compiler, but we deemed that to be a less efficient way than doing this afterwards. It is. I have also to say that this rewiring process doesn't take much. It's a very easy process. It's basically reading the assemblies, inspecting and analyzing the data, and performing the necessary steps, which are basically 3 or 4 steps, and then you're done with the existing classes.
Are you afraid of like this missing way to get viruses and other code injected?
Okay, to compromise existing code. Again, if you want to do this, you can do this. So it might be a perfect opportunity for somebody to exploit that and to add malicious code to your assembly. But again, and I have to say this here, we didn't do anything that wasn't available to begin with. It was available to us, and we exploited basically the fact that the structure of classes is not defined until they are loaded into the runtime. So we basically used a specification of a class structure and rewrote that specification. Everybody that has that knowledge can do this. And I'm not saying that it's bad or good. I think for our purposes, it was actually good. It may be bad for somebody that is concerned with security and viruses. So it's actually a loophole that somebody could use to add malicious code to your system.
Unless code signing, if you code sign your code, that does protect you.
Yeah. So
Last question.
So if you, for example, have that concern, you would use a code signing mechanism as well. So you basically you get those assemblies, and you would probably also do a code signing afterwards. We haven't explored that particular aspect, but I believe that would be possible in a fully industrial strength compiler.
All right, thank you, Marcus.